All right, for my CS50 CA application, I'm going to try and do a 5-minute crash course on recursion to make it a bit of a challenge. So what is recursion? Recursive functions or recursion is when we define functions that call themselves within their own definition. So if we look at this example, this is a bit of an abstract function, which it's not immediately clear what it does. But all that is important really is to notice that when we define recursion, this function, which takes an int and outputs an int, that within our definition for recursion, we actually use the function itself. And so this definitely seems a little bit bizarre, a little bit abstract. And I think it really helps, especially with recursion, to seek a concrete example, and then it should start making a little bit more sense. And one of the most common examples for that is the factorial. So for those of you who've done a bit of maths, or most of you will probably run into the factorial. And the factorial is simply defined on a factorial of an integer is that integer times all the integers between it and 1. So for 5 factorial, we'll do 5 times 4 times 3 times 2 times 1. And the exclamation mark is commonly used to denote the factorial. But we got something to notice here, which is going to be important when we come to code this, is that this 5 factorial is actually the same as 5 times 4 factorial. And then we think about that again, the 4 factorial, which is going to be 4 times 3 times 2 times 1, is the same as 4 times then 3 times 2 times 1 is just the same as 3 factorial. So what we really have is we can do 5 factorial. It could be the same as 5 times 4 times 3 times 2 factorial, say. So let's jump over to C and see how we can manage this. So first of all, let's try and tackle this iteratively. We want 5 times 4 times 3 times 2 times 1, or the reverse. And so if we think about this, the normal iterative way we would try and tackle a problem like this is using a for loop. And if we start with an int, we'll probably start it as 1. If we're doing multiplication, starting with 0 is not ideal. We don't want to multiply by 0 by accident. And if we go up to less than or equal to whatever our input number is, we're going to use 5 as our example, just to say I've prototyped and I've made it so it's ready to print out our results of this function when we input 5 to it. So we're going to see our results once we've written this, just to verify that we're doing it right. And we I++. And then within this, we think we want to keep hold of our results because we're going to multiply each time in this loop. We're going to multiply I by something. So we're going to need a counter. And again, like I said, we're going to want 1 instead of 0 because we don't want to multiply by 0 at any point and make some mistakes. And if we think about it, we can do counter multiply equal by 1, or I think it's maybe just a little bit easier to understand, counter multiply by I. So this is going to take, for example, when we do 5, our counter is going to be at 1, and we're going to go 1 to 5, so we're going to do 1 times 1, which is 1, and then 1 times, 2 times 1 when we get here. So then our counter is going to go to 2, then 3 times what our counter is. So we're going to do 3 times 2, 6, and then 4 times 6 is going to be 24, and then 5 times 24 is going to give us 120, or so we hope. And so here, if we return counter, that we think should do the trick. And if we'll actually verify these both at the same time. So now we're going to jump straight into the recursive function factorial, of recursive version of factorial. So to tackle this, let's think about it. Our base case that we relied on is when we try to break it down and do this, it's really important that 1 factorial equals 1. If we try to go beyond 1, we're going to get ourselves in some trouble. So if we think about it, let's just check that if we have 1, and 1 factorial itself is indeed just 1, we're going to return 1. So if we have 1 into this function, we return 1. If we don't have 1 into this function, we're taking an int, and we're going to assume that the user plays nice. Otherwise, we just have to perform a check just beforehand that they've given us a positive integer. Then what we're going to do is we're going to return input times factorial of input minus 1. And this might seem really not obvious, but let's just think about it. What does this do? If we have, again, think about our example of 5, we're going to return 5 times the factorial of 4. And when we started doing some of that scratch work in the slides, we know that this is what we want. This is what 5 factorial is, that it is 5 times 4 factorial. And then we're going to 4 factorial, where we're going to, when 4 is our input here, it's not 1, so 4 factorial is going to return as 4 times the factorial of 3, which is exactly right. That is what 4 factorial is. And that's going to go on until we have factorial of 1, and that is just going to return 1. So when we have 2 factorial, we have 2 times factorial of 1, which is just going to give us 1. So 2 factorial is going to be 2 times 1, which then is 2. So our 3 factorial is then going to be 3 times 2, which is going to be 6. 4 factorial is going to be 4 times 6, which is going to give us 24. 5 factorial is going to be 5 times 24, which is the factorial of 4. And that should indeed give us our answer. So then we look at this, do make rec. You'll see that the first result is from our recursive function. Our second result is from our iterative function. So I run /rec, which should see that we get the same result with both. Perfect. That's exactly what we expected. So we jump back into slides. We've thought a little bit about an example. So when we want to tackle recursive functions, what we should think about is we need a base case and we need a recursive call. And of course, we also need prototypes. I'm going to see why a base case is so important just in a second. Well, let's tackle that now. Why the base case is one of the things we absolutely must not forget in our recursive function. If we had got rid of this and we tried make rec again, you'll see the C compiler, give us a bit more space, gives us an error. All paths through this function will call itself, which means this function is just going to call itself forever. At no point do we ever, we're going to have, say we entered 5, we're going to have 5 times factorial of 4. It's going to go factorial of 4. We're going to keep jumping through this, this hoop over and over, just with different numbers. And we're going to run into memory issues where we overflow the memory when a stack overflow. So we must remember our base case. Otherwise, we'll run into stack overflow, and that could be issues. CS50 will avoid it for you, but if you ran that on a computer, you might crash your computer. But why do we do it then with this risk? Well, if we looked at it, this is, although it's only one line shorter, it is a fair bit less cumbersome. We don't have to worry about variables. In fact, we only have one variable, and that is our input variable. Whereas for this iterative version, we have a counter variable, we have I as a variable. We have to worry about the loops and are less than or equal to. Once you get used to factorials, this can actually be a lot easier. What if we had counter defined somewhere else? We're getting bizarre errors which we didn't understand. So there's a lot of reasons, and other than just this is simply a little bit more elegant. It's a little bit shorter, and you'll see in some other programming languages, especially if you take CS51, that recursion can be really powerful in different ways. And some algorithms, such as factorial is a classic example, are very suited to recursion, and some just don't work that well with recursion. And then one of the other downsides, depending on how comfortable you are, it might not be immediately obvious what recursive functions do when compared to their iterative counterparts. But hopefully that made sense and that was helpful as a very, very quick crash course to recursion.